right, hello to physics people. Let's learn about Ohm's law. Ohm's law describes the relationship between three quantities, which we've now all learned about these three things separately. R is resistance, and the units of resistance are in ohms. This symbol, by the way, is the Greek letter omega, which stands for ohms. V is voltage, aka potential difference. And the units of that are V for volts, and I is current, and the units of that are A for amperes. All three of these units are named after real people's last names, which is why they're kind of a random sounding word. And the equation, as it appears on the reference table, is R equals V over I. Resistance equals voltage or potential difference over current. I could not tell you why they have the equation provided to you in this arrangement on the reference table. I don't know why they picked it that way, because there are a couple of other ways to arrange these three variables that make a little bit more sense. So one thing you could do is multiply both sides by I, and if you did that, we would have the i's canceling out and I times r on this side, and you would end up with V equals I R. This is probably the most common way that this formula gets written, and maybe that's because there's no division in it. It's just multiplying two things to get the other thing, which is a little easier to think about. Definitely if you ask like my dad, who's an electrical engineer, he would tell you V equals IR. So this one has some good reasons to exist. But the one that makes the most sense in terms of physics is to get I by itself. So if we took this one and we divide both sides by R, we could get I by itself, and that would be I equals V over R. So these are just three different ways of describing the same equation. They're just solved for a different variable. They have a different one that's by itself compared to the other two. So technically, if you had a problem and you knew 2 out of the 3 variables, you could use whichever one was solved for what you were trying to find. For example, if you knew the voltage and the resistance and you wanted to find the current, you could use this one. And if you knew the voltage and the current and you wanted to find the resistance, you could use this one. So that's one reason to write it in these different ways. Although if you were to plug things in to any of them and then solve for whichever variable, you would still get the same answer. This third way is the one that makes the most sense in terms of physics, because usually the voltage is something that you control in an experiment. You use a battery with a certain amount of known voltage. You use a resistor with a certain amount of known resistance. And then as a result of these two things, some amount of current will flow. And that amount will change depending on the voltage and the resistance. Usually, you don't control the current by itself. Instead, you can control these two things, and then the current happens as a result of those. So from a physics point of view, this one makes sort of the most sense. This one is the one that's on the reference table. But they describe the same mathematical relationship, and plugging things in and solving for the unknown will work the same and give you the same answer regardless of which of these you use. But in terms of describing changing one thing and finding out what happens to an outcome, this is the one that we're going to talk about. So, if the voltage increases, what happens to I, the current? Let's think about this. If we made this V into a bigger number, we would also get a bigger number for I. And we call this a direct relationship. The first way we can answer this question is just by looking at the equation and noticing that if we put a bigger number in for this variable, we would get a bigger number out for this variable. But let's also think about it in terms of physics. So when you compare it to the air demo, the resistance goes with how difficult it is for the air to flow. The current is how much air flows. And the voltage is how hard you push. You can think of a voltage or a potential difference as being kind of the push that makes the current flow. So, let's think about this question in terms of the air demo. If the voltage increases, what happens to the current? That's like asking, if we push harder, what happens to the amount of air that flows? So think about that question and explain whether it matches this outcome or not. Okay. Same analysis for resistance. So if we increase this number R, we can tell that we're going to be dividing by a bigger number. That means we're going to get a smaller amount of current. Current will decrease. And this is an inverse relationship. In the equation, we can see that when it's on the bottom, increasing this number will decrease this number. So on the bottom of an equation always goes with an inverse relationship. Let's also think about this in terms of the air demo. If resistance increases, what happens to the current? That's like asking, if it's more difficult for the air to flow, what happens to the amount of air that flows? Okay. So if I were to push with the same amount of force through a straw with low resistance. Actually, let me grab it. Okay. So here's a straw that we discovered had low resistance. Here's a straw that we discovered had higher resistance. It was harder for the air to go through this one than through this one. So if I push with the same amount of force through this straw and through this straw, which one would have more air flowing out of it at once? And does that match the inverse relationship that we see between current and resistance? Okay, let's do some examples. You should get used to doing these examples because Ohm's law is an important equation that we're going to use in this unit and then also a whole lot in the next unit as well. So R equals 670 ohms, I equals 0.3 amps. What's the voltage? I could just use this equation and multiply these two. But I'm just gonna use the one that's on the reference table for each example, but you could use any of them that you want. So I'm gonna do R equals V over I. 670 ohms equals V over 0.3 amps. So to solve for V, I'll multiply both sides by 0.3. And I should get V equals 670 times 0.3, 201. You could write amps times ohms, that wouldn't be wrong, but the normal units for V is volts. Okay. Example 2. V equals 2.5 volts and R equals 1 kiloohm. And we're looking for the current. So V is 2.5 volts. R is 1 kiloohm. Or you can check on the reference table. Kilo means 10 to the 3. So this is 1 times 10 to the 3 ohms, or 1,000 ohms. And I want to find I. So again, I'll plug it into R equals V over I. 1 times 10 to the 3 is 1,000 equals 2.5 over I. I want to solve for this variable on the bottom. So I'm going to multiply both sides by I. That gives me 1,000 times I equals 2.5. Cancel these. And now I can do I equals, divide both sides by 1,000. 2.5 divided by 1,000 equals 0.0025. The units for current is amps. And then this is fine. But depending on what you're doing, if you're doing an experiment and you're measuring something with a meter, it probably would not give you this answer. It would probably give you your answer in milliamps. So I'm going to take this number and convert it to milliamps. I'm going to go 1, 2, 3 decimal places over. This is 2.5 milliamps. You can think about moving the decimal place, or you can think about we're getting rid of amps, we're ending up with milliamps. 1 milliamp equals 10 to the minus 3 amps. You can use a unit conversion fraction here, or you can just sort of move the decimal place. Either way, this number in amps is equal to 2.5 milliamps. Okay, there's one more. I'll walk through the unit conversions and then I will leave the actual problem for you guys to solve. When R equals 3 mega ohms, capital M is not the same thing as lowercase m. Capital M means 10 to the 6th. I equals 1.8 microamps, and this means 10 to the negative 6. And I'm looking for V. So I'll use R equals V over I. I'll plug in these. 3 times 10 to the 6 equals V over 1.8 times 10 to the negative 6. I can multiply both sides by this 1.8 number. So on the calculator, that's 3 e key 6 times 1.8 e negative 6. I'm multiplying because I'm getting rid of this on the bottom. That ends up being 5.4. Okay. So if you wanted to think about this in terms of the air demo, we have a really big number for resistance, meaning it's really difficult for the air to flow. We're pushing a medium amount. The V is the push. And then only a very small amount of current is flowing. Only a little bit of air is escaping. We're pushing a medium amount, but it's a very difficult straw. Maybe it's really packed in there with the cotton balls. So only a little bit of air is flowing. Okay. Hopefully that was helpful. We'll see how we do.